So very rarely in mathematics class, we use book as some sort of a reading exercise. But what I want to do is, I want to go section by section and try to highlight the key points. So first point that we are interested in looking at is how do we solve linear system of equation ax is equal to b. And this is the first problem typically that we deal with when we study linear algebra. A is a matrix, x is a vector, b is a vector. The second problem that we want to solve is ax is equal to lambda x. This is called as the eigenvalue problem. Extension of the eigenvalue problem is when you have a rectangular matrix wherein you have singular vectors, AV is equal to sigma u. So this is for the square matrix and this is for a rectangular matrix. Then next problem that we will do it all the time, it's some sort of optimization problem, which means minimize something called as the norm of ax. And norm, if you think about it, it's like some sort of a distance divided by x square. And the last and important problem is, given a matrix A, how do we factor it into two different factorizations? So how do we take a matrix? It could be a square matrix or it could be a rectangular matrix, and convert that into two matrices, and these matrices could be square or rectangular. And depending upon the structure of these matrices, you have different decomposition. So one important part that I want you to understand, that this problem is called SVD, which is singular value decomposition. And I'm going to spend a lot of time in working out problem on singular value decomposition. So when you come to class next week, make sure you have some exposure to MATLAB if you have not had any MATLAB experience before. And second thing is, bring your laptop with MATLAB installed. Now, what I'm going to do is, this is the gist of the introduction on page 1. The next part, which is section 1.1, I want you to understand is, we talked about two ways of multiplication. And the way we talk about multiplication is, you can actually do something called as the inner product and you can do something like an outer product. If you have studied linear algebra in the past, most likely you know about inner product. But when you talk about the outer product, what it means is you separate out a linear system of equations into its basis vectors and make sure that the right hand side vector is within the span of those basis vectors. And if you don't understand and if you have any questions about some of these comments, just raise your hand and I would explain it to you. So the most important part that I want you to see in section 1.1 is quickly look at example 1. In example 1, the author shows two ways the multiplication can be performed. And the most important part that the comment here is, as long as the third vector in the matrix. So if you think about it, if you have a matrix And the first vector maybe is 1, 2. Second vector is maybe 0, 1. But if the third vector is 1, 3, please understand this matrix has only two independent columns, because the third column can be obtained if I were to add these two. So which means, since there are just two independent columns, the rank, this is a very important word, rank of the matrix is 2. By definition, rank is number of independent columns that is equal to number of independent rows. So the next statement in this entire section that is important is AX is the linear combination of column of X. What does that mean? It means, suppose if you have a matrix 1, 2, 3, 4, and you multiply that with a vector x1 and x2, then what's going to happen is this equation, this whole equation can be, if you were to visualize this whole equation can be written as, and we talked about this in last class, 1, 2, x1 plus 3, 4, x2, which means whatever solution that we are going to get, and this is super important, and that is what is the meaning of that sentence. Whatever solution that we are going to get is the linear combination of these two basis vectors. Everyone understood this? That's what is author trying to explain. And that concept is super duper important, because let's imagine that I'm trying to solve this equation. So 5, 6. My objective here, and we talked about this in last class, my objective here is to find out the values of x1 and x2. Very important, because there's an example worked out in next section. So I'll point that to you. What it means is you have x1 and x2. Those are some numbers. They are not vectors. They are scalars. They are numbers. This vector multiplied by this number plus this vector multiplied by this number gives you this result. That is only possible as long as this particular pair of numbers, 5 and 6, is within the span or the range, so to speak, of these basis vectors. If that is not the case, then x1 and x2s cannot be found out. And I'll show you an example wherein we talk about something called as the null space. Null space means the particular location that is not reachable no matter what combination of basis vectors we choose. That is out of reach. So what it means is, if you want to go to a location along the z-axis, no matter how much you travel around x-axis and y-axis, you will never get to z-axis. So that is what it means. And null space is super duper important. So there is another important concept which is called as the column space, which is again discussed in section 1.1. What do I mean by column space? So this is the first column. This is the second column. So column space of A, C of A is actually 1, 2, and 3, 4. This is what is called as the column space. Then the important part that comes next is what is the row space. And now you can tell me the row space is instead of 1, 2, it will be 1, 3 and 2, 4 because those are the rows. So column space is vertical columns, row space is horizontal rows. Now, what I want you to do is, I want you to quickly look at example 2. Now, in example 2, what I want you to notice that for that particular combination of vectors multiplied by matrices, you cannot find x1 and x2 such a way that all three equations are satisfied. So what author is trying to say in that case is this is very easy. You can find out the values of x1 and values of x2 so that you can get solution 5 and 6. However, imagine something like this. So imagine now I have a matrix where I'm going to add one more something, say 2, 4, and instead of 5, 6, I will have 5, 6, and 4. Now it is very difficult to find values of x1 and x2, to find out values of x1 and x2, so that the first equation is satisfied, second equation is satisfied, and third equation is satisfied. You agree with me? Does it make sense? If any of this doesn't make sense, just raise your hand and ask. There is lots and lots of information contained in the textbook that we need to decode as we actually move forward. So what exactly is going to happen is, that is what is explained in example 2. That means if you take these two equations, yes, you can find x1, x2. You take these two equations, you can find x1, x2. These two equations, you can find x1, x2. But you cannot find x1, x2 when all these three equations are valid. Everyone understood this? And this is a major problem. Why? Because, and you see now I have a rectangular matrix, a rectangular vector, and I need to find out some sort of least square solution. So convert that rectangular matrix to square matrix, do the inversion, and find a point which will not satisfy all three equations exactly, but it will satisfy these three equations approximately. Everyone understood this? So that is what is discussed in example 2. Now the next thing the author talks about is what do we mean by subspaces. And when you study linear algebra, at least advanced linear algebra that we are talking about, you will always hear this word subspaces, subspaces, subspaces. Because if you think about it, every entry in the matrix is visualized as a vector. It is very easy to visualize a two-dimensional vector, x and y plane. Draw a line, vector is drawn. Easy, actually, you can extend that to 3 dimensions, x, y, z. Draw a line, that's the vector. But think about 5 dimensions, 6 dimensions, 7 dimensions. We cannot visualize it. But that is what is meant by subspace. That is the space spanned by the vector. That is the space where that vector exists. We may not be able to draw it, but mathematically that space exists. And then he talks about if you have x, y, and z. So if you have x, y, and z, what are the different subspaces? So the different subspaces they talk about is the zero vector, which is the point. Then it talks about the line of vectors. This is one line, the combination of these two lines, so all the points here, and combination of these three vectors, so you can have a three-dimensional vectorial representation. And if you have a three-dimensional subspace, basically we call it R cube. So this is first real line, second real line, third real line. R stands for real. If you have R1, this is called as R square. If your line has complex, then usually they say C2 or C2 or C cube when the line is complex. And I want to move on to next page, which is page number 4. That is where this concept, the entire section talks about the concept of independence, which means if any vector, and when I say vector, any column, if any column is expressed as the linear combination of constant multiplied by the first column plus a constant multiplied by the second column gives you any column or third column that is not linearly independent. Linear independent means everyone is unique, everyone is independent. There is no relationship whatsoever between the previous columns and the next column. And this concept is super duper important. Why this concept is super duper important is you may not realize this, but the systems that we deal in physics, they have some interdependency or some independency. A clearest example which I can talk about, and it comes next, is think about a chain. Think about a chain. As you can see, these links of the chain, this is the first link L1, this link L2, and this link L3, they are sort of independent. What it means, this is very important, L1 can move without any association with L2, L2 can move without any association with L1, and L3 can move without any direct association with L1 and L2. So that they are independent. On the other hand, if you were to look at the structure or the chain or the maybe this is called as the network. If you have L1, L2, and L3, you can see L3 is dependent on L1 and L2. So what it means, and we will talk about it, when we try to express the tree or a graph or tree or a loop inside a matrix notation, you will easily see that matrix, if we use that to represent the tree, it will be independent. If you were to represent using the loop, you will see dependence. And that is the basis. That is the basis of search algorithms. And even whenever you play chess or if you play any type of strategy game, you'll always notice the game engine will go through the tree or through the structure. Finally, at the end of the day, a big matrix will be solved. So every possible moves, and I'll show you. I won't be able to do it for the chess, but I will show you for a very simple case where by looking at the structure, you can construct a matrix. And once that matrix is constructed, most likely it's going to be a rectangular matrix. How would you choose which move to make? You will do singular value decomposition and find out the most dominant part of that matrix and use that to decide your move. That is exactly how Google will give you results based on page rank. Every page rank, when it's constructed, something like an incidence matrix is derived, because in terms of, if you think about the very basic of page rank, so it will choose a keyword on the web page and see how it is linked to the web page that is somewhere in the internet. And then this billions and billions column and row matrix in multiple dimensions gets solved to find out the most optimal path or the most important search result. Yeah. I did not follow how this is linked to matrix. Huh? I did not follow how. Can you explain? Yeah, yeah. I will actually explain that with an example. Just bear with me. But what I'm trying to say is the concept of independence and linear dependence and independence has some physical interpretation in structure. That is the point I'm trying to make. But I understand that that is a tricky concept, and unfortunately that is not explained when we study linear algebra, but that is coming next in the book. So just bear with me for 2 minutes. The rank is number of independent columns, which are equal to number of independent rows, is all the discussion in this section. But important part here is if you have a matrix, and I'm not going to ask you to do this. So for an example, if you have a matrix A, this matrix can be represented as a column matrix multiplied by the row matrix. So this is a column matrix and this is the row matrix. So this is the decomposition where you have an A matrix that can be split into a column matrix and into a row matrix. And when you multiply these two matrices, you get the matrix that you start with. And then author talks about the ways of doing this C times R decomposition. And the whole purpose of showing this decomposition is, even though you may have a matrix that is big and ugly or fat, or if you have a slim matrix, you can always split that matrix into two parts where it is easier to understand and solve the system of equations. So that is what is being discussed. And then you have problem set 1. So this would be a great time after going home to take a look at assignment number 3 and work out a few of those problems that I have listed on assignment number 3. Everybody understood this? And again, I don't expect you to come find the solution completely. You are welcome to attempt those problems. And if you have any questions regarding solution of those problems, you are welcome to ask me in class, and I will try to help you as much as I can. But I would suggest that take this moment to start attempting the problems from assignment 3. The next part is actually, it talks about column space, rank of the matrix, which is the summary of what we talked about so far. Second section is super simple. This is matrix and multiplied by matrix multiplication. So if you look at what we have discussed so far, I just told you that if you have a matrix, if you have a vector, you can do sort of outer product multiplication. You can do the exact same thing with the matrices. And that's what is being shown over here. But the most important part that is confusing is these called index notations. And index notations are very common when you look at maybe machine learning or artificial intelligence, where you can express a very long expression in terms of very simple or second coordinates. So I just want you to take a look at the index notation that is explained over here. So that is critical because sometimes when we talk about it, you have, give me a second here so that I can plug in my old card. So you have something called as I. This is your I. This is your J. And what we want to do is we want to somehow expand this. So this is secondly represented as K is equal to 1 to 3, A 2K, then you have B 3K. So if you were to expand this, what that means is you have A 21, B 31 plus A 22, B 32 plus A 23, B 33. So that is what it means. So I want you to see, and most of you have had some experience with computer programming. So I want you to run this list. This is simple. The problem happens when it is represented something like this. And I will explain it to you in just a second. So you have sigma, and you have outer sigma, and you have A, I, K, B, K, J. You have K running from 1 to 3. Then you can have I running from 1 to 3. And you can make this super complex. So I'll say J running from and I running from 1 to 3. So what this means is first you have to expand the inner indices K. Then for each value of K, you need to expand J. For each value of J, you need to expand I. So which means this is a super long expression, but it's represented in a very short notation format. So this may be confusing because sometimes authors like to use this type of notation. Sometimes they call it Einstein notation, but this is something that you want to be careful about. Now the next part, which is page 11, is those 5 lines are super important. So these are called the most important factorizations. And factorizations means you take a matrix and split it into 2 parts. So the first so if you look at the first factorization is something called as LU. And I'm not going to ask you to do these factorizations. Perhaps if you had a mean linear algebra teacher, he or she might have asked you to do these factorizations by hand. It's not fun. Maybe for 2 by 2 or 3 by 3 you can do it. But for actual problems, doing this factorization is very, very painful. But what this means is taking this matrix and converting into a lower triangular form and converting this into an upper triangular form. And why all this lower and upper triangular form factorization needed? Just to make our life easy, so that we can solve million by million set of equations using some simple numerical linear algebra techniques. Next important factorization is A is equal to QR. So where in A is equal to QR, this is Q is orthogonal. So they are ortho. And this is actually very commonly called as Gram-Schmidt. So Gram SCHICHMRDT. And again, I'm not going to ask you to do this QR decomposition. We have MATLAB to do LU, we have MATLAB to do QR. But the most important physical insight that I want you to get here is, if you have a matrix, as soon as you convert that into something which is orthonormal, the solution becomes simple because now your basis vectors get perpendicular to each other. So you may have an A matrix. Last time when I gave you an example, it was super difficult for us to see how those vectors are resolved because the basis vectors were not perpendicular. As soon as you have some sort of orthogonal decomposition, once the basis vectors become perpendicular, it's very easy to see which vector is important. And there is some more insight to this QR decomposition. Is if you think about it in terms of basis vectors, and if you think about it, this R matrix, you can think about it is like weights on those basis vectors. Which means if you have a matrix, and if you want to find out what part of matrix I should keep and what part of matrix I can discard, you will need some sort of decomposition. So here, once you do this decomposition, and I will show you one example. So unfortunately, it is very difficult to visualize or understand what is the practical significance of this unless we work out some problem in MATLAB. So next time, what I can do is when we go to start working on MATLAB, I will actually show you where the QR decomposition is actually used. Then next decomposition is a famous decomposition where you have sort of eigenvalues, and S matrix is called symmetric matrix. And what is the purpose of symmetric matrix? You have some elements on the diagonal, but the elements here are the same. So the off diagonal elements, they are the same. So essentially, you can draw. So let me give you an example, a very simple example. 3, 4, -2, -2. If you were to fold this matrix along the diagonal, as you can see, the off diagonal terms are exactly the same. So this is why it's called as the symmetric matrix. Now, what is the fundamental property of the symmetric matrix? The fundamental property of the symmetric matrix is eigenvalues are real. Eigenvalues are real. Real means they could be positive, they could be negative, but eigenvalues are not going to be imaginary. Eigenvalues will be real. There is a special case, and that is Professor Gilbert Strang's favorite matrices. Those are called symmetric positive definite. So what is this symmetric positive definite? In symmetric positive definite matrix, the eigenvalues, it's again symmetric, but the eigenvalues are all positive. They are real and positive. So as you can see, then the next decomposition we talk about, and I need to write this down, which is S is equal to Q transpose, where S matrix is symmetric. And then you have our famous eigenvalue decomposition, which is A is equal to X inverse. And last but not least, you have counterpart of eigenvalue decomposition for rectangular matrices, which is U sigma V transpose. So this is our friend SVD. This is eigenvalue. Then the next part of this discussion, it talks about something called as the spectral theorem. And spectral theorem, again, what it means is, again, it's actually shown in bold. Spectrum theorem says every symmetric matrix has n real eigenvalues and n orthonormal eigenvectors. So that's exactly what we said. For symmetric matrix, you are going to have eigenvalues that are real and the eigenvectors which are orthonormal, not orthonormal. That leads us to problem set 1.2. Again, same thing. I would encourage you to look at the assignment 3, and then in assignment 3, there are some problems from problem set 1, 2, and try attempting it. Some problems are super simple. Some problems are actually filling the blanks from the textbook. So as long as you know what section it belongs to, if you read the section, you can fill in the blanks easily. Some problems are actually more involved. The next part is 4 fundamental subspaces. So what this means is something simple. So if we have a matrix A, I'm interested in knowing something called as the column space. I'm interested in knowing something called as the row space. I'm interested in finding out the null space which is associated with the column space, and I'm interested in finding out the null space corresponding to row space. So those are the most important fundamental subspaces. And it may not be evident at this point why this distinction is super important. And this is very important because when we try to look at the numerical linear algebra, or for that matter, applications of linear algebra to machine learning and data sciences, these fundamental subspaces play an important role when we look at the solution. And if you look at the the uh, the highlighted section, which is, it actually defines what a column space is, then what the row space is, what the null space is, and then what is the left null space is. And I would encourage you, strongly encourage you, to look at example 1, where you have a matrix and author solves the problem showing you how to find column space, null space, and so on. Similarly, you can look at example 2, and example 2 is an excellent example where you can show, where author shows where what happens when the vector is in null space. And then he tries to explain actually graphically by plotting those vectors. So that is what is talking about. In example 3, this is what I was talking about. And this example is interesting, and I'm going to walk you through it because this is very important. Now, I want you to look at the graph that is drawn below. Can you see that there are 4 nodes, x1, x2, x3, and x4? So let me ask you this. How many of you know what a traveling salesman problem is? Does anyone know what a traveling salesman problem is? That is a classic problem. So imagine something like this. There are 4 cities denoted by x1, x2, x3, and x4. And a traveling salesman has to travel across all those cities. So basically, he can take the path B1, he can take the path B2, he can take the path B3, he can take the path B4, and he can take the path B5. So basically, this travel and those cities, they form something called as the network. And this network can be very nicely represented as a matrix. So how is it represented as matrix? So what I want you to do is, I want you to first look at x1 and x2. So in that, so I will draw this here. So I want you to look at x1, x2, x3, and x4. And I want you to note that this B1 is going from x1 to x2. So I want you to see the first row of the set of equation. Can you see minus x1? Minus x1 plus x2 is equal to b1. What that means is when the travel is from node 1, node 1 is a starting node, node 2 is the end node, what you have is b1. So that is the edge. So this is the node. So you have minus first node going to second node, and the edge is b1. Now I want you to repeat this exercise for x1 to x3. If you look at the edge b2, b2 is going from x1 all the way to x3. So you have minus x1 plus x3. Continuing that on, you have b1, b2, b3, b4, b5, and you recognize that you have this network. And believe it or not, this network could be the network of flows. For example, fluid flow, like flow to multiple pipes, or it could be network of electrical currents, or it could be just a social network like Facebook, where you know that the user 1 is passing on some information to user 2, and user 2 is passing some information to user 4, user 4 is passing some information to user 3, and that way you can actually construct this big matrix, which is called as the incidence matrix. Everyone understood this? So what it means is, if you have a network problem wherein you have incoming flows, outgoing flows, or if you have social network, or if you have some sort of a business transaction, all those can be represented as the matrices. Now I want you to look at the difference between the figure shown and the figure I have drawn. Now let me ask you this. I want you to look at the figure in the book and the figure that I have drawn. What is the difference? I have 4 nodes, x1, x2, x3, and x4. How many edges do I have? 4 edges. Now, can you see that these 4 edges, these nodes, can go away from each other or can come closer depending upon B1, B2, B3, and B4? Do you agree with me? Do you agree with me? So would it be right for me to say that these edges are sort of independent right now? Because basically there is no additional constraint. You can actually, that node can go left, that node can go right. That's totally cool, as long as there is no middle edge. So once I add this, can you see that I'm losing my flexibility? And the reason I'm losing the flexibility, because I have this x2 x3 connection. If I were to change, the length of any other edge, that connection, x2 to x3 connection, gets broken. Why does it get broken? Because inherently that connection is dependent on 2 connections that are on the top, or 2 connections that are on the bottom. Which means if you were to construct the matrix the way it is, one column is going to be dependent. Why that column would be dependent? Because in physical network, that if you were to think about that road, is dependent on the road on the top, the 2 roads on the top or 2 roads in the bottom. And that's exactly is happening. So if you look at the matrix, which is just on the right hand side of that network, if you type that matrix in inside the MATLAB and you say rank, you will see that it's ranked even though the size of the matrix is 1, 2, 3, and 4. Basically that my matrix will have rank 3, which means the number of independent columns will be 3. And that is what is explained in the loop and the tree. As soon as you have a loop, then you lose independence. If you have a tree, the vectors or the representation, you have independence. And on page 18, this is where all comes together. So basically, if you talk about the row spaces, the column spaces, and the null spaces, different techniques in data science, different techniques in machine learning and artificial intelligence, they utilize these spaces and the algorithms pertaining to these spaces. The next part is fairly simple. That talks about what happens to the rank when you add the matrices or when you multiply the matrices. Key observation here is what you see, that is the observation that is in the highlighted. So if you have rank of AB, so rank, and then there are 4 statements, and these statements pertain to rank. Then you have problem set 1, 3, and I think I have included 1 or 2 problems from this problem set, and I would encourage you to take a look at these problems and ask me if you have any question. Next part, elimination A is equal to LU. That is basically you take a matrix and convert that into 2 parts, or convert that into 2 matrices. One is a lower triangular matrix, another one is an upper triangular matrix. So what I want you to do is, author has gone through this exercise to show you, like, graphically what that means. And believe it or not, I actually showed you this in the very first class. So I think I solved the exact same problem. So there is something called as the row picture, wherein what you have is you have 2 lines that intersect, and the point of intersection is the solution of those 2 equations. On the next page, you have something called as the column picture, wherein what you want to do is you want to make sure that the resultant is the linear combination of the basis vectors. Everyone remembers the very first class I talked about the row picture and the basis vectors. So that exactly is repeated in figure 1.4 and 1.5. And next part is just going through a mathematical technique. Let me see if there are any questions. Yeah, the mathematical technique to solve AX is equal to B by elimination. And I trust this is the problem that probably you solve when you take the first basic linear algebra class, wherein you go through some mathematical jugglery and try to find out the solution. But we don't have to do this. We are going to use MATLAB to solve equation AX is equal to B. If you move on to the next section, that actually shows you how to do that decomposition. So you are welcome to take a look at that, but we are not going to use hand calculations to solve problems, because you can do LU decomposition for 2 by 2, 3 by 3. As soon as you go to 5 by 5, 10 by 10, LU decomposition is not possible. But it would be instructive to look at the problem that is worked out, and then I think I have asked a couple of problems from problem set 4. So to solve problem set 4, I don't expect you to use, and make a note of this, I don't expect you to use the hand calculation. You can just use MATLAB and get done with it. That's totally fine. The next section is orthogonal matrices. Orthogonal matrices means rows are perpendicular. So a classic orthogonal matrix is 1, 0, 0, 1. So that is a very classic orthogonal matrix. And you can see 1, 0, 0, 1. And why this is orthogonal matrix? Because if I were to draw the row vector And if I were to draw, so this is 0, 1, and then I have 1, 0. So, so these two vectors are perpendicular to each other. And I showed you in last class, if you were to take a dot product, the dot product basically gives you 0, which means the angle between these two vectors is 90 degrees. So that is all talked about in section 1.5. So how do you find out if two vectors are orthogonal or not? How do you find out the orthogonal basis? And then the definition of orthonormal matrix. So orthonormal matrix, and I just want to give an example. If I want to invert this matrix, you agree with me, A inverse is again 1, 0, 0, 1. If you don't believe me, use MATLAB, which if you do A transpose, which is again 1, 0, 0, 1. And what is the reason? Because not only the basis vectors are orthogonal, the determinant, and the determinant is this multiplied by this minus 0. So 1 multiplied by 1 minus 0 multiplied by 0. So determinant is 1, which means not only the vectors are perpendicular, but the determinant of the matrix is 1. That's why this is called as orthonormal matrix. And in case if you are wondering, I will not ask you to calculate the determinant. If we need to calculate a determinant of a matrix, we'll use MATLAB. And just so you know, I don't know if you have looked at it, in the very first assignment, there is a MATLAB webinar or a MATLAB course that talks about basic linear algebra using MATLAB. And I promise you, whatever you have studied in your undergraduate linear algebra will be covered. All the concepts will be covered in that 2 hours course, but you won't be doing with hand calculations. You'll be using MATLAB to find out eigenvalues, eigenvectors, determinant, rank, and all that type of stuff. So please do those courses. The next part, orthogonal matrices, we talked about it. So there is a Pythagorean theorem for matrices, when what you do is you basically find something called as the norm or the total resultant or the distance. And author talks about how to do it. So Hadamard matrices are super important. They are used in signal processing and wavelets. We will not talk about them right now, but maybe talk about them later. And the last part, towards the end, which is page 31, we talk about, the author talks about the big picture. So again, the 4 fundamental subspaces: row space of A, null space of A, column space of A, and null space of column space, corresponding column space, and the how the transformation occurs. And this may sound little complex or look little complex, but once we start looking at the data science applications and machine learning applications, it will be very clear that how the algorithms are operated or how the algorithms work based on what type of space you're operating in. The next part is it talks about different types of matrices, fat matrices, thin matrices. At this point, I am going to ask you to look at example 1, which is on page 32, because I know for the fact that in assignment 3, I have asked you exact or similar example. So in this example, what the author is doing, he's showing you multiplications using the column technique that we talked about, and actually trying to plot where these vectors are and what they mean. So please try to understand this. The next part, and this is where robotics meets linear algebra. I want you to take a look at the, the, the page number 33. Does it look familiar to you? If you are in my robotics class, what is it? It is the rotation matrix. And basically that rotation matrix, the key observation here is the rotation matrix is an orthonormal matrix. And I will use this fact in the next robotic class where we will be inverting the rotation matrices. So rather than inverting the rotation matrix, I would just transpose it and say, hey, we are good. And I would like to take this moment to tell you what that means. Think about it. And there might be some students who are not in the robotics class, but bear with me just for a second. You have frame number 1 or frame number 0, and you have frame number 1. So basically 0 or 1 will take you from the 0th frame to the first frame. But now my question is, I want to go from R1 to 0. So rather than going from the 0th frame to the first frame, I want to go backwards. What is the best way to go backwards? Inward. So what happens is R01 is 1 R0 inverse. But finding inverse is computationally super intensive. So I'm going to say, rather than inverting, I would actually transpose. That is computationally much easier. Okay. So clearly, that's why I said bear with me if you are in this class, but not in the robotics class. So R01 is a rotation matrix wherein you are going from the 0th frame to first frame. Now, if you want to go back, if you want to go from the first frame to 0th frame, you have to invert the rotation matrices. And since rotation matrix is orthonormal, you can get away just with transpose. Yeah, Joshua, unfortunately, these are the concepts I just discussed in my previous robotics class. So don't worry, we are not going to use that in this class, but I just wanted to make that connection. So don't worry about it. So, or I can give you access to my robotics course, and you are welcome to watch my robotics video. As a matter of fact, if you Google SS Redcar YouTube, you will see my entire robotics class and rotation matrices in the videos. But that is just for FYI, not required for linear algebra class right now. Okay, next part is reflections, householder reflections. So I wouldn't worry about it, but those are important when you try to solve signal processing problems. The next part is problems on page 35, section 1.5. Again, basically, author talks about the permutation matrices, where author talks about something called as the wavelet matrices. So basically, how do you represent wavelets with matrices? So section 1.6, eigenvalues and eigenvectors. And I think I spent a lot of time, and as a matter of fact, I covered eigenvalues and eigenvectors in a lot more detail. But in this section, author talks about the complex eigenvalues. So if you have a matrix, and when you try to find the eigenvalues, you land up with something like square root of -1, your eigenvalues would become complex. But don't worry, MATLAB is your friend. Say EIG in the parentheses A, and it will give you eigenvalues. The next part is how do you diagonalize a matrix? And diagonalization is a very interesting process. So for an example, I'm going to show you something, and I'm going to do an exercise on Tuesday. on MATLAB that will actually show you what happens when we diagonalize. But if you have a matrix A, if you say in MATLAB Mn is equal to Eiga, this will give you eigenvalues and eigenvectors. So if you want to diagonalize, you can use the eigenvectors M inverse AM, and you will realize that if it has independent eigenvalues, you will see that this matrix will be diagonalized. It may not be evident at this point why this is important, but believe you me, all the material that you studied in your differential equation class, okay, is contained in just one single expression. Whatever you have studied in your undergraduate differential equation class, I know you might have studied a lot of stuff, separation of variables, some tricks, strict substitutions. All that stuff is contained in this simple approach. But again, this is not a spectator sport. You cannot learn swimming by watching YouTube videos. So what I'm going to do is I will walk you through it step by step, and then you will realize, why did I take that differential equation class if all that knowledge is contained in these couple of lines? So bear with me, it's coming next. So next part is how do you diagonalize? And then you have problem section 1.6. And I don't see any problem. You should be, as a matter of fact, I have asked you some true or false questions. So those true or false questions, they directly come from the text. But you have to be Sherlock Holmes and you have to comb through the sentences to find true or false. Sneaky. So it makes sure, I had to make sure that you read the textbook line by line. The next part is symmetric positive definite matrices. Symmetric matrices, top part is equal to bottom part. You can fold the matrix on the diagonal. Positive definite means all the eigenvalues are positive. Symmetric matrices, eigenvalues are real, but they could be negative. For symmetric positive definite matrices, the eigenvalues have to be positive. Everyone understood? Or was that too fast? Just read through that 3 pages, and that's what it talks about. So yeah, so test number 1, which is on page number 45. Positive definite matrix has all positive eigenvalues. And then he talks about energy-based definition that I'm going to talk about in a lot more detail. And I will discuss this. Next part is he is going to talk about, if you look at the next part is, if you go to page number 50, the author is trying to make the connection between the linear algebra and machine learning. It's something good to read, but right now it's not really required, because I will talk about this in a lot more detail on how linear algebra is associated with optimization, how is linear algebra is associated with machine learning. That being said, I would encourage you to take a look at the singular value decomposition. I8, this is probably the most important section in this first lesson. And I talked about the singular value decomposition, which is similar to eigenvalue decomposition. Only thing is the matrix is rectangular. And then in the next part, he talks about proof. Unfortunately, I'm not a mathematician, so I'm not going to run through proofs. But I will use MATLAB to solve problems. And the next part is talking about SVDs of derivatives and integrals. That is right now not needed. So the last part is principal component and best row rank matrices. That is where you are given a big matrix, and how do you find out the most important part of that matrix, which is exactly the image compression algorithm that I talked about. So how do I find out the most important component? Please read through this. It may or may not make sense because unfortunately, unless we do this in MATLAB, it will not appeal to you. So just read through this material, but I will take concrete examples and I will share MATLAB code in next class, and we will do principal component decomposition on very large images. And with that, I'm gonna stop here. Next class, please come prepared. There is going to be MATLAB. So I'm gonna stop here. And if you have any questions,